Okay, let's do a gravitational recap. Again, I say this is not a replacement for reading your notes, so please read your notes as well. Okay, so let's start. Okay, we look at the four basic formulas in gravitation first. The first one is force, which you know is gmm over r squared. Right, if I were to be interested in the field of, let's say, the bigger mass, right, I'll take this force divided by the mass of the smaller mass. Right, so that leaves me with the mass of the bigger mass in the equation. Right, so it's gm capital M over r squared. This is the gravitational field due to large M. Okay, so force and field are both vectors, so the negative here actually implies direction. Okay, so this is significantly different from your energy as well as potential, which are scalars. Right, the negative here has a different meaning because potential energy, gravitational potential energy as well as gravitational potential are both scalars. Right, we'll discuss more about this in graphs, right, which we'll do in a separate video. Right, so for the scalar negatives, just remember, can never be removed. Right, for gravitation, there is no case whereby these scalar negatives are removed ever. However, these negatives in the vectors can be removed depending on the situation, depending on the diagram. Right, since these actually are directional negatives. Okay, so with that, we can look at the formulas for potential energy and potential. Okay, potential energy, the formula is minus gmm over r. Right, potential energy is always between two masses. So when I talk about gmm over r, is the potential energy between these two masses at a certain distance r away. Right, r, okay, just to be clear, is distance between the two center of masses. Right, so just be careful of that. Okay, so finally we talk about potential, which is potential energy divided by mass, right, of the other mass involved. Right, so if I'm interested in potential due to big M, right, I'll take potential energy divided by the mass of the smaller m. Right, that leaves me with minus gm over r. Okay, so what other relationships do we have to be aware of? The relationship between force and potential energy is F equal minus du dr. Right, the relationship between field and potential is G equal minus d phi dr. Realize that this one is actually comes from this one. Right, force divided by small m become G. Right, U divided by small m become phi. Right, so actually these two equations are related. Alright, so we move on to look at certain special case type of gravitation questions. Okay, there are two special case type of gravitational questions, more or less. Alright, one is orbits, two is escape speed. Right, for orbits, you actually require some circular motion knowledge. Alright, so what happens in orbits is I have some mass or some planet, normally it's Earth, can be other planets as well, right, and I have some satellite orbiting around the planet. Right, so with this satellite orbiting around the planet, the only force acting on this satellite actually in such a system is actually the gravitational force, right, Fg, which is what I draw here. Okay, there is no case in which your centripetal force should be drawn on a free body diagram. I hope you realize this by now. This knowledge should fall under circular motion. Right, so Fc should not be a force drawn on this diagram. If this were to be a free body diagram of the satellite, only Fg should appear. And what is this? This gravitational force. Okay, it's quite common to be asked to find out what the kinetic energy of this orbiting satellite is. For that, we use this equation. Alright, so remember that for a question that asks you to derive or prove, you have to give some physics meaning associated with the equations that you use. Right, therefore, look at the way I structure my equation here. Gravitational force of Earth on satellite, which is this Fg here, is a force acting on the satellite, equals to centripetal force required to keep the satellite in circular motion. Right, so this is the Fg is the centripetal force. Right, they are the same thing, and that's the reason why you cannot draw Fc on the satellite again. Right, because Fc is actually Fg, they are the same thing. Alright, so gmm over r squared, right, where r, okay, maybe I should replace this r by small r. Okay, so this small r, right, this distance is small r. Okay, so gmm over r squared is the Fg acting on the satellite, and this equal mv squared over r from your circular motion. I can make this half mv squared. Right, I cancel this r with the square. okay, and I half both sides, right? That's where the 2 come from. I half both sides. This becomes half mv squared. And realize that this is your kinetic energy of your orbiting satellite. Right, with this I can actually find the total energy of this orbiting satellite. Total energy is always given to be GPE plus KE. Right, so GPE is given by minus GMM over R. Right, you should know just the distance R away tells me what GPE is. Again, the negative here cannot be removed at any point of time for gravitational potential and gravitational potential energy. Right, so we already know KE to be half GMM over R. Right, the half here actually comes from the 2 here. Okay, so when I sum this together, my total energy of an orbiting satellite will be minus GMM over 2R. Right, so this total energy for an orbiting satellite. Okay, what other types of questions? There's the escape speed style of question. So for escape speed style of question, they normally ask you what is the minimum energy required at a certain position to escape to infinity. For this type of questions, we like to use conservation of energy to solve them. Okay, realize that if I have a mass over here, right, and this is the planet, right, and a small mass that's trying to escape. Okay, at this position, which is my initial position, I have to move towards infinity such that for me to go to infinity rather, I must have a certain minimum kinetic energy. Okay, what is that? So we can look at conservation of energy to explain this. Okay, the initial energy here will be given by half mv minimum squared, okay, where v minimum is what I'm looking for, right, minus gmm over r. Again, remember this negative cannot be removed because it's potential energy. Okay, so minus gmm over r, which is the potential energy of small m at this position, okay, equals to the final energy. The final kinetic energy where at infinity must minimally be 0. Right, so I sub 0 for kinetic energy. Right, as long as I can reach infinity at 0 KE, I'm fine. I will have escaped the Earth's field, and therefore I will have escaped from the Earth. Right, so final KE can be substituted to be 0, and at infinity, my GP can be given by minus GMM over R, where the R is actually infinite. So this one actually tends to 0 as well. Right, so realize that your total energy at infinity minimally should be 0 for me to escape. Okay, it could be more because actually this value could be higher than 0. Right, but because I want minimum escape speed, so I sub my kinetic energy at infinity to be 0. Right, my kinetic energy cannot drop below 0. Right, minimum KE is 0. Right, so I have this equation now over here. Right, realize I didn't change the left hand side at all. Right, but the right hand side will be 0. My total energy at my final must be 0 for me to calculate escape speed. How you want to manipulate this equation from here is up to you. I do not recommend memorizing V minimum formulas. Okay, you can simply derive it this way.